Okay, thank you for the introduction. Reflecting on what I should present, I wanted to tell you this time I will stay completely in the discrete world, so everything will be really just MATLAB without reference to the continuous variable cases. However, everything is embedded into my standard picture, the minimal situation. Normally I'm saying, well, the situation is like rational numbers, real numbers, complex numbers. Rational numbers are where you do the computation. Real numbers are nice because they are complete. So what is 1 over pi? Well, it's an irrational number, and you tip it into the computer or so, you know how to do it. But you never do these infinitesimal approximations. It's always the question that up to some resolution, decimals, you want to know what 1 over pi is. So 1 over pi is an abstract object, the multiplicative inverse of pi, and you can do approximations and you use rational computations. But if you want to understand the addition theorem for cosine and sine, you think the exponential law is so easy and take real part, imaginary part. That's so in the level of complex numbers, you understand everything. So that's my view now on this space is a good space of test functions. That's a space of continuous integrable functions. So the short-term Fourier transform is integrable, and therefore you get all the good properties. Everybody can see it's clearly invariant under rotations by arbitrary angles. That's why I choose a circle symbol. That means it's fractional Fourier transform invariant. It's contained in L2 as a dense subspace, and if you take the duality, you have a so-called Banach-Gelfand triple. Now, we are learning, or we're teaching our students in mathematics that there are discrete signals living on the integers, there are periodic signals living on the torus, there are finite sequences which living on the unit roots of order n, so that each of these signals lives on a different group. But on the other hand, the periodic signal is ongoing. You can think in the old way of painting the wall. I mean, we say, look at the waltz. Waltz is the right object. But if I see a pattern on the wall that repeats itself, it's also something, a two-dimensional object or so. So in this setting here, you can have discrete signals. They have a Fourier transform in the distributional sense, which is, of course, the discrete Fourier transform, and all these other things work quite well. But here you have weak star convergence. Now, weak star convergence looks a little bit weird at first sight, but it just tells you that you have information up to some resolution. I think of nowadays, signals are really objects in this domain. Signals are objects that you can allow to do a short-time Fourier transform. So if we take my sound, the sound of my voice, I could take the microphone and I could show you the spectrogram. Who can get the pointwise values almost everywhere? Could we have a discussion if it's L2 or LP? That's all, for me, meanwhile, nonsense. Almost all the signals that I can think of, like room temperature or so, in the physical sense, there's something, you take local averages and you have some information, of course, yes, but it's something that you can measure with a certain way. And I think now, these are the signals and these are the measurements. So the pre-dual are the measurements, and that's also going nicely because the measurements should be linear, of course, and the conjugation in the short-term Fourier transform is going in the test function. So if something has a short-term Fourier transform, you can correlate it and you get something bounded, a bounded spectrogram. That's one definition of this here. But when you want to do approximation, you have to approximate it from here to here. So you look at this piece of music stored on the CD is 3 minutes, 0 to 20 kilohertz, a segment of this. Pictures on your camera are approximations of the continuous reality, which at the very limit really doesn't exist, but up to some resolution. You can have a high resolution camera, a low resolution camera. So that's my understanding. So when we would discuss, which I stopped now, everything at the level of finite, then you discretize this here. And there are theorems with Norbert Keiblinger that if you do a piecewise linear interpolation of your data sequence that you sample, then you can approximate the function S0 in the sense of S0, which means in any of the LP senses. That's kind of the background, and that's why it's necessary to do all these things, not for fixed resolution, which I do in this experiment and which I did for years. So what is a good signal length? So I was choosing always 480. Why? Because it's large enough that pictures look nice, like continuous ones, but also it's not like 512, a poor guy who has very few divisors. 480 has many more subgroups, and when we talk about Gabor analysis and subgroups, the variety is much better. Nowadays, I would probably take something like 1200 or so, any of the numbers which have a lot of divisors. By the way, 44,100 is a very good number. It's 2 times 3 times 5 times 7 squared. So all the possible combinations allow you, so for people in number theory. Okay, so at the end, I decided to start the presentation more or less from the end, because I'm afraid by talking so much, I would not come to the end. And I will explain later how we are doing this. So my standard setting, as I said, is signal length is 480. And in order to show the effect of different time and frequency lattices, I'm choosing, of course, divisors. So I have discrete subgroups with a lattice constant 20 and 16. That gives me a lattice, I don't show it, with 720 points, which is a redundancy of 3/2, a very simple redundancy. So it's 1.5 as many Gabor values compared to things. So it's a frame like my 5 fingers in R3. It's a frame of redundancy 5/3 in R3. So that kind of idea. I also will need to mention that I'm working, and there are many good reasons for this, with row vectors. At the beginning, it was like the intuition of a medical person. I mean, the medical doctor would look at some picture and the next one and the next one. So you have one signal and the next one. So that was my original motivation. But meanwhile, it turned out, and I can, of course, demonstrate it, if you work with row vectors, your matrix has to act from the left. And it's much, much faster in MATLAB. And the explanation is, of course, naive, harmless, is if you write matrix with vector, matrix with vector, column vector, MATLAB says, okay, I have a matrix with a matrix. Matrix multiplication is expensive. And once you have the product matrix, you apply it to the vector. So you could speed up by making brackets. Whereas if you take a row vector, apply it to this matrix vector multiplication, another matrix vector multiplication is fine. Also, if you have 2 column vectors, x and y, and you want to do the scalar product, there is no command in MATLAB. You take the x and the y, and you make the y conjugate and make it a row vector. So you have y prime with x. In the row situation, you say x with y prime, you do this. So we are actually very, very close to the bra and cat notation, and I'm also trying to explore that. MATLAB is very much like bras and cats. And I would say, for me now, the signals are the bras, the objects which can undergo a measurement, which is a cat. And if you have an operator in between, then you just can throw it on one or the other side. Okay, but the reason is now, if you are taking the scalar product of a vector, so now maybe I should write this at least. So I'm describing a rank 1 operator, xg, for example, the projection on the vector x would be x with this, and in MATLAB it would be x with g prime with g. And of course you can use associativity of matrix multiplication, so the matrix, of course, is cat with bra, is the rank 1 operator. So, of course, in the Gaussian case, I have a discrete Gaussian. This is also a 2-dimensional Gaussian. And I have a unitary version of the Fourier transform, just showing you that it's made such that this Gauss function is Fourier invariant. I also use for quite a few years now a command which allows me to compute discrete Hermite functions. And the idea was, I think it came up during a talk in Oberwolfach. They said, well, I can build multipliers, and it's not so hard to make a radial symmetric weight in the discrete case. So if I take a Gabor multiplier, so I take a Gauss, more or less I think I'm going to Fock space and multiply down. I take a smooth version of an indicator function of a circle or superposition, and I get, so Hermite functions of order n are a system, an orthonormal system of Hermite functions, the eigenvalues. This is the Gabor multiplier coming from the weight and the weight. So that's how I computed it. It's very fast, I don't want to show it. Here I show you the Gauss function that I'm using here. And this is, for example, I don't know, Hermite function number 23 or something like this. So the spectrogram of one of the Hermite functions. The only thing that you would like to see is it's really rotation invariant. If I increase, if I take the Gauss function, it's the most concentrated thing. If I take the next Hermite function, the radius would grow. The thickness of the graph would be always the same. That's because it's always with a discrete Gaussian window. Therefore, the area of these things goes up. I could compute the 0 norm or M1 norm. It would grow like n over 1/4, but it's more and more flat. So the dual norm, the sup norm of these pictures would go down with n to the -4. Okay, so yeah, here is just demonstrating a centered image of the weight that I'm using. It's really just the ordinary radial symmetric weight. There are different routines, just to tell you. I started to call the routines Gabor multiplier with coefficient sequence or upper symbol or Berezin symbol or so W, and that's this radial symmetric decaying function. And MH is Mario Hampais, who was one of the first people to do an efficient, and I had another version. It shows you that the weight that is used is not exactly one of these routines, but done in a different way, but we can do it in different ways. And to jump right away into the current workshop, I think I was doing it for the Trondheim workshop. I said, well, all the things, these convolutions are so I can do quite easily. So FOPKNS means function with operator, so convolution of a function with an operator using the Kohn-Nirenberg symbol. I have to mention that something, I mean, the name Werner Kotzek has been mentioned already. He was the one who was teaching me, coming from mobile communication, what an underspread operator is. An underspread operator is, in terms of communication theory, not a convolution operator, which is a moving average, but it's a moving average with slowly changing profile. So it's like this, and while you go, here's like this. People in pseudo-differential theory would say, oh, I'm not describing the operator at this point by this impulse response, but I'm taking the Fourier transform. So I pretend that the value here is taken by some transfer function. And then there's some other transfer function at the other position or so, and I assume that this is not changing too much. So this is the Kohn-Nirenberg symbol. He was also telling me that I should try to stay away from the Wigner calculus, and so because of the difficulty with discretization. So Kohn-Nirenberg symbol, spreading symbol, is easier to do in the discrete case, at least at first sight and until very recently, I would say. The problem is that the e to the pi e to the I pq is the square root of the e 2 pi I q, and the square root with even numbers is not a very good thing. Okay, so I just want to continue here now with a timing routine. So that's something just mentioning. A timing routine, if I do the different methods to create the same operator, that's the point here, it's comparable. And I actually have not checked exactly what I'm using now for computing the other, but sometimes it turns out that certain routines are kind of quite clear what you're doing, but it's very slow. For example, if you take a Gabor system, the dual family is nothing else but the pseudo-inverse of a big rectangular matrix transpose conjugate. Okay, very easy. But when you have a big system, then that takes a lot of time. And it's, of course, very much better to compute the dual Gabor window with an efficient method to solve a positive definite equation. And so that's why I'm routinely, when I have different implementations, I try to see. So here you see these three routines, including the one, and that's really the quantum harmonic analysis. I'm convolving the weight function once more, and that's why I put it here. I'm convolving the weight function, this radial symmetric decaying bump function, with the projection operator. And I'm getting exactly the Gabor multiplier. And the next thing is kind of leading me. I thought, well, I've heard about this Fourier-Wigner transform, and the convolution of operators goes into multiplication on the Fourier transform side. So that's kind of more or less what we do here. So my setup is, or my understanding of the situation, either in the continuous or in the discrete setting, is we should say, well, there are these objects. Here it's, functions, square functions, general functions. But I could say, no, this L2 has two variables. These are the Hilbert-Schmidt operators. Then, of course, the Feichtinger algebra are the Feichtinger operators. But you can take all these operators which have a kernel in S0 prime, and then I say, well, these are exactly the operators which map the good functions, the test functions, into S0 prime. Also this I was undergoing a change of my own mind. As most of us, I was accepting that when you work with operators, trace class operators and Schatten classes or so, I mean, the universe is always the most general operators. And what are the most general operators? The bounded operators on the Hilbert space L2. But then I realized, well, there are so many operators that we use for engineering applications that are not like this. The easiest example that I have is take a sampling operator. You start with a decent function in S0, and you sample a discrete measure, bounded discrete measure or so. Maybe you are even combining a sampling with periodization. So somebody is giving you the Gauss function. I'm saying, okay, now I'm periodizing the function. You're getting a bounded continuous function. And then I start sampling. If I'm not completely naive, I would say, let the period be an integer, for example, and the sampling rate a fraction of an integer, so that it doesn't matter whether I periodize first and sample afterwards, or I sample the function and then the Dirac comb is periodized or so. These are clearly operators that are mapping only from S0 to S0 prime. And when you look at, any operator can be manipulated. So any such periodization sampling operator must have a spreading symbol. It's not very deep to find out, well, it's just the periodization is a periodization in time, and sampling is periodization in frequency. So the spreading symbol of an operator which does a very coarse periodization and a very fine sampling is just some object which has a nice spreading representation. And that can be used and displayed also in the finite setting or so. So coming back, the Fourier transform is the symplectic Fourier transform, as we have heard, and brings us from the Kohn-Nirenberg symbol, this time variant transfer function, as engineers would call it, to the spreading function. I think for the explanation, it's maybe easier to say a spreading function is a representation of an n by n matrix as a superposition of n squared time frequency shifts. We have n cyclic shifts, we have n frequency shifts, n squared combinations. And if you look at the matrix representation, a diagonal modulation operator is a diagonal matrix. If you shift it, it's two pieces, and then you have pure frequencies. So if you take the Hilbert-Schmidt norm, which is nothing else but the Euclidean norm on the pixel space of matrices, you see immediately there an orthonormal system. So an orthonormal system of n squared time frequency shifts in the n squared dimensional algebra of matrices is of course an orthonormal basis. And the spreading function is exactly the orthogonal expansion. Another way for me that I don't show here is when you are then saying what happens if you conjugate a matrix with time frequency shifts. Then you're doing your algebra or you make a small MATLAB experiment and you see, oh, it's like multiplying with some plane wave. So I was conjugating with time frequency shifts 3, 5, and I was taking that factors and taking a two-dimensional transform, and it was getting, instead of 3 and 5, I was getting, I don't know, minus 5 and 3. And I say, well, I would like to have 3 and 5, so you have to flip the variables. That's part of the symplectic Fourier transform. And you have one forward, one inverse transform. And so for me, the symplectic Fourier transform is very natural coming from the properties of the spreading representation. Okay, so I have the idea that in the, this line here, we are looking now at the convolution of operators. It's a little difficult here. Here, this convolution of operators with a symbol. I have to take a random signal now. But now I'm at the operator level. Now I'm looking everything at the spreading representation. So I'm going from operators to with mat2 spread to the spreading domain. And what I see here is I'm getting two symplectic Fourier transforms. So the starting description was the A, that's the Kohn-Nirenberg symbol of my operator. And the symplectic Fourier transform is the spreading representation. So spreading representation of this is the Fourier-Wigner transform in the previous presentation. I have to multiply in the pointwise sense the Fourier-Wigner with the symplectic Fourier transform of this. And then I just apply the inverse of the mat2 spread. That's kind of make from a given kernel, from a matrix, the spreading representation. I'm going back just to eliminate the mat2 spread. So what I'm doing here is spread to mat. So what is one possible way to realize this convolution? I'm saying, you give me an operator. I'm computing this object here, which is the spreading representation, and there are fast algorithms. I multiply it with the symplectic Fourier transform of the function, the weight here, and then I'm going back and make a matrix out of it. But at the end, it's just, if we stay at the Kohn-Nirenberg symbol, it's just convolution. If I go to the spreading domain, it's just pointwise multiplication plus identifications. And in the same way, you can say twisted convolution is, well, these pixel images correspond to operators. We know that operators are represented by matrices, and we have multiplication of matrices, which is composition of operators. So twisted convolution, taken back to the kernel theorem, is just convolution. So that's kind of actually how I implemented my twisted convolution. Okay, so now I try to go. What I'm doing next is a demonstration. I have my Hermite system. I'm using it for just now. And I take a low Hermite function, a trigonometric polynomial of the first 190 Hermite functions, just to have something well concentrated in time and frequency. And I want to demonstrate what I can do with a fractional Fourier transform, which is a rotation, which is more or less multiplying these Hermite coefficients with phase factors, which are pure frequencies. That's all what I'm doing. And I'm showing you the picture in the spectrogram level. So just look at this a little bit, and then you will see I have rotated by 30 degrees using this, and it's a perfect reconstruction. I mean, maybe at the boundaries you see some minimal changes or so, but You can use the LTFAT toolbox, and there they also have such commands. And you will see that there are much more deformations. So I'm quite sure that my discrete Hermite system is much better. The other thing is understanding that Gabor multipliers are like convolution products arising in quantum harmonic analysis. What if I take a random signal and multiply it? There's now really localization operator with a circulant filter. So I'm taking the short-term Fourier transform. What I'm getting here is this object. So you see, the interior is completely reproduced. Most of the details, of course, at the boundaries, there is some smearing effect going on, like a convolution with a narrow Gauss function. So the difference here is, in this first example to the left, I have composed it from the Hermite functions. That's really an orthonormal, I could say that's also an orthogonal projection using the Hermite system. Whereas in this case, it's not an orthonormal projection because we know it's not a perfect symbolic calculus. There are problems with the boundaries. A 0-1 template, that's this circular domain, has eigenvalues which are constant 1 in the interior, a drop-down region which is more and more narrow if you have good Gabor systems, and this is the output. And of course, you can do a Gabor filter. You can cut out by any domain. So here I was choosing a rectangular domain. I just take a Gabor expansion and take the coefficients inside some rectangular. So kind of these are, I would say, for me, the kind of applications that I have in mind. Now I'm going to the plotting routine, kind of little comments about the toolbox and the tricks. I have a lot of kind of private, or of course I'm sharing it, commands. When you have a Gaussian, a discrete Gaussian, to make it Fourier invariant, I've already shown quickly, it's invariant under the discrete Fourier transform normalized with 1 over square root of n, so that it's unitary, otherwise it cannot be really numerical invariant. But I obtain it by taking an ordinary Gauss function. You tell me what your n is. So in this case, I'm not sure, probably 480. I'm periodizing it, and I'm sampling it. And in order to get 480 values, I have, of course, to take square root of 480 as a period, and 1 over the square root as the sampling rate. Now you have the Gauss function, which is so small that I don't see it. Maybe the Gauss function is sitting here, and then the rest is so small that you don't see it. But in principle, I'm saying, well, this is supposed to be a discretized, periodized, discretized version of a Gauss function. Because we know the continuous Gauss function is invariant, and because sampling goes to periodization, and periodization goes to sampling, and 1 over something is the number, this is really a discrete function, and plotting it from 0, where I'm plotting it from 0 doesn't look good. So engineers say, well, we plot it from here to here and take this data set. That's also not good, because then the Fourier transform will be highly oscillating. It's shifted by half the signal length or so. So the data should be such that the first value is at 0. It's Gauss function at 0. 1 of sampling step 2, 3, 4, 5, and then you go back. That's how the plot is done. So kind of I'm using the correct data set in the group theoretical sense and so on. Now there is something that I don't show you. I have had it in the slides in Trondheim. A very important step is to go, what if you increase the information? So you have more information about the function, and the easiest step is to say, well, I quadruple the information by doubling the period and doubling the free sampling rate. So instead of having a period p minus 1/2, minus p half to p half, but sampled in this way, I do it now with the bigger period and every sample. And what will happen, of course, you have 0, new small step, old, new, old, until here. And there are a lot of zeros, and so on. So you have to have a routine grabbing from a sequence of length 4n, a subsequence of length n. And what I can tell you, just mentioning, is with the discrete Fourier discrete Hermite functions that I have, this is completely compatible. So it seems that when I increase from n to 4 and 16n or so, I'm just getting more and more values, which is a clear indication that if I do a smooth interpolation, I would have really good approximation of the discrete Hermite functions. Okay, yeah, the plotting routines, for example, that's kind of things that I'm using is low signal is simply a low frequency signal, so it's a trigonometric polynomial. For simple display, I was choosing signal length 72, maximal frequency 7. So what you see on the F2 spec is, well, let's look at we compare two functions, two signals, and how they look differently on the time and the frequency side. So what you see on the right-hand side upstairs here is 7 random coefficients. And then you take the inverse Fourier transform, you see real part, imaginary part, always plotted with the center in the middle. And the Gauss function, you see, that looks quite similar, and actually it is. What took a while to implement, and I don't play around, but this representation is much more nice because it tells you really a function on the torus is paper on the cylindric, and you can rotate it or so if you do it separately or so. And if you show this to students, it's kind of, they start better to understand that there's no clear beginning and you have to choose the beginning in the correct way or so. So kind of that, and you see here, of course, the real imaginary part of this low-pass signal or so. The next thing is at 2 dimension. I take now the 2-dimensional Gauss function, which is the same as the projection operator, and make the image of it. In MATLAB, it's this. And of course, if you apply the FFT shift, then you have to put the correct labels. Then you could put it in the center. And if you zoom, you see it more clearly or so. Again, the data structure is this one, and the display that I'm using all the time is this one. And the idea is sometimes I'm showing, well, take this as a tile, buy it, and put it on the wall. The Kronecker construction is easy to... Then you will say, okay, there are always at the crossing points, there's nice flowers, which you put in the middle for visualization, but not for the data structure. And of course, the 2-dimensional Fourier transform or the symplectic Fourier transform of the 2-dimensional Gauss function is like this. That's another repetition. Now, I have a command called show mat4. Maybe I just, yeah. Show me a matrix in 4 different settings. And the convolution operator is a very good example. We all know that a circulant matrix represents a convolution operator is something constant along side diagonals. Okay, that's left upper. That's the matrix representation of the convolution operator. When you are asking what is the impulse response, then you say, well, apply it to the unit vector, the first unit vector. So that's the first column of this matrix. And then you see that depending if you take rows or columns, it would be easier to explain everything with rows, but traditionally it's columns. But you can also say, well, I do it on a Fourier basis. So I conjugate that circulant matrix with the Fourier transform. And then, of course, I have taken a smooth function. Therefore, it's a diagonal matrix with not so many non-zero entries. But essentially, general convolution matrix would be a diagonal matrix. It's kind of, oh yes, if I take an underspread operator, it would have columns which are slightly changing as you go through this, and it would have a tridiagonal, multi-diagonal situation or so. Now, in the spreading domain, we all know a convolution operator can, in the discrete setting, is a sum of translation operators, a weighted sum of translation operators. The coefficients are exactly the entries of the impulse response up to some harmless flip or so. So In the spreading domain, it's a pure time frequency shift. So if you have something which is a slowly varying channel with this changing thing, it cannot be represented as this because all those translation operators are only giving convolution operators with a fixed profile. Hopefully, in practical life, mobile communication, things are not too bad, and locally they are behaving like convolution operators, blah, blah, blah. But an underspread operator would be something where the spreading function is concentrated here very much. And that's, in this case, it's a Kohn-Nirenberg symbol. That's kind of a symplectic Fourier transform of this here. And you can imagine something concentrated here would be have a Fourier transform in the vertical direction. But because we changed once more the flip, we have this. So, yeah. Now, of course, for many years we have routines that allow to compute, given a Gabor atom, the corresponding dual Gabor atom. And here I compare three things. A discrete Gauss function again, n equals 480, a equal 20, b equal 16. Redundancy 3/2. So with the a little bit larger than the b, that's so to say the message. Then the dual looks like this. The Fourier transform of the dual looks like this. But the Fourier transform of the dual is the same as the dual of the same with the changing the lattices. So I could say, well, here, if the A is a little bit larger than the B, then you get such a thing. And if the B is larger than the A, you have such side lobes. Roughly speaking, you can say, well, assume you are having information that most of the information in the Gabor matrix is the diagonal part. If A is big, you have a Gauss function, let's say. If the Gauss function is squared, it's even more spiky. If A is big, then something going down, and going up, and going down, and going up. If you invert this, you get these negative dips. If you're having the opposite situation, you have a relatively broad Gauss function, and you try to make a bi-orthogonal thing by linear combinations of shifted Gauss function. And you say, well, I have to take away the side lobes, I have some negative. But because it's too deep now, I have to take positive, and so we go this sync type pattern or so. So this is telling you a little bit about this. And of course, you can take a tight Gabor window, which is s to the minus 1/2, and it looks like this. You see from the sharp spike to the inverse spike, it's flat. I don't know actually that somebody has proved it, but it might be useful. And when I do, for example, Gabor multipliers, I go for reasonable low redundancy, use redundancy for tight things, then I know that if you feed in constant 1, you get identity operator. If you have now a symbol which is changing slowly, you're getting something which is quite good. And where the discretization in phase space is okay. This was something that I did just in the break now. I thought it may be interesting to show you the spectrograms of a random signal, kind of, yeah. This is a random signal where you see the blue dots are the zeros of the short-term Fourier transform, nicely spread out, approximately n of them. And then I took the spectrogram with respect to Hermite function number, well, it's 0, 1, 2, 3. As you see, there's some nice patterns, or so maybe it fits to the talk of Daniel. Yeah. Yeah, right, yeah. Yeah, okay. Yeah, for me that's at least plausible because we are displaying the absolute value of the short-term Fourier transform, but we would see the same pictures when we took the spectrogram absolute value squared, because big values are bigger and so on. But if you would take the cumulative sum of the spectrogram, you would have a spectrogram with a rank 4 operator, which is quite good. I mean, I only put one more thing. This is, yeah. Yeah, I don't see the command. Oh, yes, here, the last command is. So display in the usual centered way. Now, not the short-term Fourier transforms, but the short-term Fourier transform of a subspace. And the subspace is generated by you can take any system of vectors, because this first step in the routine is, well, make the projection operator on the subspace. So essentially do an orthonormalization of the system, but here it's already an orthonormal system of dimension 100. And then you're trying to do the localization of the subspace. So it's what I'm really doing here is nothing else but to take the short-term Fourier transform squared, or the spectrogram of the first function, the Gauss function, Hermite function number 1, 2, 3, 4, up to number 100, all this squared. Now, at one given place, you know that the sum, the Hermite functions are an orthonormal system, the sum of all these things will add up to 1. And so if you have kind of this is this most concentrated, significant of the most concentrated function space with 100 generators, which is most concentrated. And if you're trying to add more, if they're orthogonal, they must be such that the sum of what you have already with what you add is not more than 1. So where can I stay close to the center but outside of the red region? Because there is almost 1 here. I have to stay around, and that's why the next Hermite function is closer and closer and closer and closer. And I can, of course, take a similar experiment, and I think I have to come to an end, with the general profile. So usually I'm thinking of a smooth upper symbol. So it's a landscape like the region where I'm living, Weinviertel. This is agricultural area for hundreds of years. It has been carved out many, many times. So it's a smooth, hilly area. And so if I would like to see the concentration of the eigenvectors of a Gabor multiplier or an anti-Wick operator, I would say, well, there was millions of years ago, there was a sea here. And then the water went down. And when I wait at some moment, maybe the area of the island was 25. Then I would say, well, the total concentration of this 25-dimensional subspace generated by the first 25 eigenvectors of my Gabor multiplier, which is very same as the anti-Wick operator in many ways, is exactly this shape. And I think that's something where we have to see a lot or have to do a lot of work still. I mean, I'm happy now that I can do so many things. I'm taking not every, but challenges. If you say, well, can you compute this and this? I definitely will try it. But then what you see is, and what is plausible should also be verified in a practical, in a I don't know, numerical way, functional analytic way. What are the function spaces? I would say, of course, modulation spaces, but I think that's kind of this was the discrete side of what we are discussing in more theoretical terms in the rest of the week. Okay.